everyone.
Good evening, Dr. Calix. How are you?
I'm doing good, thank you. Okay,
Fantastic.
great. Welcome. So let's get started. This is ITS450. You should be able to see the whiteboard at this time. Just a few reminders. So homework, the first homework assignment was due last Thursday by 10. So you should have submitted your homework assignment. That was on the Set UID lab. And then this Thursday, you have your format string vulnerability lab. That's going to be due again by 10 p.m. And then currently we'll be working on the buffer overflow lab. So what's so great about these labs is that they all go together. It's kind of a sequence. And we're really now, hopefully if you'll be submitting those two assignments. So we're just going to be working on this last one. Okay. On this last one, which is the buffer overflow vulnerability lab. So I started explaining this last week. I started explaining this during the last Tuesday lecture and Thursday. I went over the details of the lab. I'm just going to continue that today and Thursday. But basically that should wrap up all the fundamentals of the lab, and then you can just work on it. Okay? And really, once we complete these three labs, we've completed our sequence in CC++. Right? Remember, our course is software assurance, but we've been focusing a little bit on C and C++ at this time by doing the set UID.
Good boy.
Set UID format string, and now the buffer overflow. Okay, so that's a sequence of labs, and we just need to wrap this one up. So I really just want to make sure that all the concepts are clear. So today what I will do is I will go over all the details. I pretty much laid out everything already. As we've gone over the idea of memory and the stack, we already covered that in great detail. And then I've gone over the vulnerable program also in a lot of detail. And so now I'm really just going to wrap it up. And then hopefully once you complete the three labs, you'll be ready for the assessment, right? So I'll talk a little bit about that. As you know, we are currently on week 4. So this is week 4. And that means that we've got exams coming up, right? So we've got our first exam, we're going to have 2 exams related to this. We're going to have a written exam, which will be on week 6. So that's September 29th, I believe, the Tuesday. So the Tuesday of week 6, that's going to be a September 29th. So mark it on your calendar. That's going to be the day that you have to do a written exam. Obviously, it's going to be online somehow, and so we will figure that out. And then I'm still trying to figure out when we're going to have the practical exam. So if you remember, the practical exam is also it's also an in-class problem about these 3 things. So I'm going to give you an in-class problem. And during that period of time, basically, a fixed period of time, I will open the Dropbox, but it's only not like I usually give you a week. This is because it's a type of an examination, you have to have a more limited period of time to solve just one problem. It's literally just one problem, and I will give you some help with it, but a good understanding of these 3 topics will definitely help you to solve it, right? It's not just a written exam. You actually literally have to get a root shell in order to succeed. Does that make sense? Okay.
Yes.
Yeah.
Yep.
No questions. So we're going to do then just reminders again, written exam coming up September 29th. And then the practical exam really just depends on when you guys are ready for it after you've submitted these 3 labs and we've had any discussions about them. Possibly it would be the week, that same week, week 6. So that it would sort of make sense to do it on October 1st, for instance. And so the written exam on Tuesday, the practical exam on Thursday. So that's a possibility. Okay. But we need to finish the labs, so that's why I don't know how much you've worked on the labs. It's possible that the 17th of September is the first time that you will work on this buffer overflow lab. You definitely, though, need to get started with that one, right? So if you're falling behind on the other 2 labs, you need to talk to me, see me, just to make sure that everyone is on track. Okay, so before I get started with today's topics, are there any questions about anything I just said?
Nope.
No questions. All right, great. Remember, you can also read in the book. It's going to be the chapter 4, the buffer overflow attack. So you can take a look at that. There's a lot of information there and in the PDF. Okay, but it's pretty much everything that I'm discussing in the class. And then I've also posted some slides on Brightspace, and I'll get to those. Usually when I post the slides, it means that I'm doing a type of summarization of some of the topics. And so we will be doing that as well. Okay. Yeah. So take a look at chapter 4. Some great information in there. All right. So so let me move to a new slide here. So as you know, the buffer overflow lab involves a little bit of looking into the details. Of understanding how memory works. And so one of the first things we did is we looked at the stack. And so we looked at the stack, and I've explained all of that. I've gone over the structure. I've gone over how a function can be mapped into the stack. Okay, then we have arguments and local variables. So I've talked about the frame pointer and how you create a frame in the stack. We've talked about that. We've talked about the return address and where it's located. And then we did the example of, having several functions, or even a recursive function, and how that can be represented in the stack. So we've done that exercise. Then so we finished pretty much our discussion of the memory layout, which is very significant to what we're doing. And now, then later I covered the vulnerable program itself. So we talked about how the lab has actually 2 programs. So then the vulnerable program. Okay, we talked about the vulnerable program. And basically, we identified that the main problem is that our input, which is user controlled, is a lot bigger than the target where we're writing our data. So we have a source and a target. The source is much bigger than the target. Therefore, we use a function, string copy, which is not a function that provides bounds checks. And so therefore, you end up overwriting spaces in the stack. And because the stack can have a fixed structure, we could end up actually overwriting the return address, and that creates a big problem. So we talked about the vulnerable program. We explained how that mechanism works. And then we started to look at, okay, if we can overwrite the address in memory, which address do we give it, right? So if we have that power to magically just insert an address, that's great, but which address do we insert? So that's the second part of the problem, right? So we needed to come up with a solution for that. And so what was the solution that I suggested last Thursday? So, you know, we talked about the address and how to put the address in memory, but then which address do we use? So what was the suggestion?
Return address.
Say that again?
Return address.
We can put the return address, sure, but which return address? A return address just means that that's the address that when the function finishes executing, it'll look at that address and jump there for the next instruction, right? So we can give it any address in memory, in the computer's memory, but which address makes the most sense to give it? So that's, you know, we need to understand that because that's how you're going to be solving your lab, the practical exam, everything. So which address do you give it? Any ideas? You guys don't remember? So we said that, remember that we were doing a code injection, right? Like a little train. And here was the return address. And then I said that we would do no ops. Oops. But then if you remember, I wrote that something could go here. So what was the thing that I suggested that you could put there?
Shell code.
Shell code, very good. Very good. And what is this shell code? Can you tell me? What is shell code? It's the machine code of a program that generates a shell or a terminal, right? So we had that in, when we looked at the PDF, you had the very first problem was just, hey, take this C code, compile it, run it a couple of times in these two different ways, and convince yourself that both times, the one that's just pure C and the one that's a code that actually launches a machine code, that both of them would actually result in a terminal. Do you remember that? That's really important, guys. So if you don't remember that, certainly go back to the video and take a look at it, because these are the two, there's these two ideas, right? Most of the hard part is just creating this code injection. That's really the hard part for you. You're going to create a buffer of size 517 or so, and it needs to have this specific structure where this address, the return address, aligns with the address in the stack. Remember, this is the stack. So so now I ask you this other question. If I'm injecting this code in the stack, right? Because this is the stack, and I'm injecting the shell code there. Now, which return address do I use? How do I know where to look, not specifically, but just what address would I use?
Is it the shell codes, like where it is?
Yeah, exactly. Wherever this shell code is in the stack, that's the address that we're going to use. Very good. And it doesn't actually have to be exactly that one. To increase the success of this, we can actually decide that it's going to be a range, right? And we can actually get an address somewhere in this range. And it's as long as we have no ops in here. Why is it okay if we have no ops? What are no ops?
Does it mean
Okay, go ahead.
ignore that section or something?
It's a what?
Is it something like you just kind of like ignore that section or?
Yeah, the no op is an instruction in the CPU where you're going to, as the name implies, no op, no operation, but you're going to take a step in the stack. So if the pointer is here, you do a no op and boom, it moves there. Then the CPU reads that no op. Oh, okay, nothing but move. Oh, okay. Then it reads this one. It does, oh, no op, does nothing but moves, and then boom. Once it hits this, what's it gonna find? It finds the shell code, and it's gonna execute that sequence of commands, and if you're successful, you're going to result with a shell, okay? So that's sort of a summary of what we were doing last week. So now we're gonna emphasize this a little bit by talking about the challenges of the attack. Challenges of the attack. So, you know, I'm repeating this a lot, but try to picture it in your head and certainly start working on the lab. Right? So what we have here, remember, is we have the stack, and then we have the frame for that given function. So this is the frame pointer. Okay? And so in here, we're going to have, so this is the return address. Okay? And then remember that we have a buffer here. That's the code that we talked about. So we have buffer size 12. Okay? And these are addresses that we have. That's an address. Okay, and the address space is actually quite limited. It's not very, very long. So the challenges are number one, how to get code, how to get the code into the memory. Right? And the other one is the address. And I would argue that getting the address is actually the hardest part. So this is pretty straightforward because I already showed you. You just create this. Save it into, you know, in the lab, we're going to take that file, save it into bat file. And from there, you'll be able to launch the attack. So that's doable, but it's really getting that address that's going to be a little bit more challenging. So how do you find the address to the malicious code? Okay. All right, and so that's really the specific challenge that we have. Okay, so one of the things, so we're gonna, that's pretty much it actually. So at this point, I have really finished a lot of the details of this. And now what I'm gonna do next is just start going into the specifics of the lab and how we can solve it. So that's really where I'm gonna go in and just give you a lot of details, some of the commands. And my goal is that you guys will start working on this lab and just, you know, ask questions basically. Okay, so let's now think in terms of the lab itself. Okay, so the buffer overflow lab, the basic idea. And let's kind of frame it in how we're going to do it. We will first turn off several security mechanisms. Right? One of them is called stack overflow. There's another one about not allowing code that runs in the stack, right? So I can't remember the name of that one right now, but not, you know, the executable. Disable executable stack, let's call it. And then you'll need to disable address randomization. Which as the lab indicates, you know, address randomization is that you would basically put the stack in various places randomly. So, you know, initially, you know, you run it one time, the address is, you know, let's say the stack is really long like that. So one time the whole stack is there, but then another iteration it's there, then another iteration. So learning that stack address would be pretty complex or useless really, because if we only do this one time, we learn that it was here, we use it there, but now the stack is over here. Then the next iteration, we use it here, but we realize the stack is over here. And so for now, you know, we're just going to turn that off. Later on, we're going to learn how we can enable that and still get to break this. But for now, we're just going to disable it. So that's the first thing. That's the basic idea. Then we have two files, exploit.c and stack.c. Exploit.c simply creates bad file. And then stack.c simply reads. So this one writes and creates it basically. This one reads it. Okay, so that we don't have to type that really long code injection of size 517. Instead of having to do that, we just conveniently read it from bad file. And this one then, bad file holds the custom code injection. Code injection. And remember that our goal is to gain root privileges or root access. Now, again, we go to exploit.c and stack.c. The program that contains the vulnerable program is stack. So this contains the vulnerable function. Because this is a function, stack gets, everything about it gets stored in the stack in memory. Just like that. It gets stored in the stack in memory. So our target will be to overflow a buffer in stack.c. So that function will contain, in stack.c, will contain a buffer. As I said before, what stack.c, after it's compiled, tries to do is it tries to read that file. It reads that code injection, right, into, so you are reading literally, you are reading the contents of that file into buffer. You can try buffers of different sizes, like 24, 12, whatever, but just keep in mind, this one has a fixed value of about 517, given the program that we are using. All right, so our goal then, exploit, and stack, actually I should say, stack is all ready to go. So stack.c, if I remember correctly, does not need for you to modify anything really about it, significant. But the program exploit.c is incomplete. You remember there, it kind of initializes the buffer. I think it does a mem set for no-ops, which are 0x90s. And that's the instruction that means a no-op. So it mem sets it to that. But then, and then it shows you like when it's done, but you guys have to write this part. So you have to put in the return address and the shell code in there. Okay, so that has to be written into that. So remind me, either you work it out yourselves or remind me to give you this, okay? You know, ask for help if you can't figure it out. Okay, and I'll help you out to put the code in there. Now, I ask you the following question. If you run stack and stack overwrites, or sorry, the program stack overwrites the stack, and then the CPU gets the address, jumps, gets the address here, jumps to a place in memory, executes shellcode, and gets a terminal. But will that terminal be just a regular user terminal or a root terminal? And if so, so I'm trying to answer this question, what kind of terminal do you get? And then how would you get the root terminal, given what you already know from the previous labs? Because that's really what you want, right? You don't want this one, you want that one. So how do you get this one and not that?
Let the root on the stack.c program.
Okay, very good. You said let root own. So let's say I've compiled it now and the owner is root. Is that all I need in there? That the owner should be root?
I should execute.
It is executable already.
Oh, okay.
Is that enough? Is that all the elements?
It needs the set UID as well as the owner root.
Yes, very good. It also needs to be set UID. Excellent. All right, so that's very important. Now, based on your set UID, even if it was set UID, it was root own, it was executable, did it work? Or did you have to do one additional thing in order for it to work? What else did you need for it to work?
Another process.
Hmm?
Need to add in another process, right?
Not
Like we-
another, not another process, no.
Okay.
But we did something for it to work. To get the root shell in the SetUID lab, we had to do something. Even if it was root own, even if it was SetUID and executable, we still had to do something to get that root shell. What was that?
Did we have to change it, like the permissions on the file?
The permissions, I mean, if we make it
It's a
SetUID and root own, yeah. But what else? There's one more thing. What was it? As you can see, I'm just walking you through the lab at this point. I'm not really, because we already covered all the theories, so I just want to make sure everything is clear. So what else? What else? Remember, what I'm asking is, in the SetUID lab, how did you get the root shell? What did you have to do?
Execute the shell code.
In the SetUID lab, you didn't have shell code.
Okay. The SH.
Ah, SH, what about it?
/ZSH and press enter.
No, not that.
Okay.
Is it
We
something
had-
link,
Yeah,
having to link it to? Hmm.
we linked it. We linked
Yeah.
SH. We used to remove the symbolic link of SH to bash, and we removed that, and instead we linked it to CSH. Remember? Yeah.
Yes.
Why did we do that?
I think because Bash has security in place.
Yes,
to
bash
prevent
was
it.
more secure, right? And whenever you have a process, and then somebody runs like another terminal to break out of it and create another process from it, bash doesn't allow you to retain the effective ID of root. So here, the effective ID of root over here becomes seed. Right? Do you guys remember that?
Yes.
Yeah, we discussed that. Now, the first time that you do this, you will only succeed if you do the same thing that you did in the SetUID lab, which is to break that link to bash and use CSH. And then you'll get the root shell. However, as we will see in this lab, even that mechanism of bash could be bypassed. And so, but first, I want you to do it just like you did it in the SetUID lab. Once you guys have completed that task, then I will say, okay, this is what you need to do now in order for you to actually break it both without, regardless of bash or CSH. Okay? Does that make sense, guys? Right, so I will be giving, as I go through this walkthrough of the lab, I'm going to give you a lot of hints or commands, actually. So just, make sure you ask questions. All right, so one thing that you might have an interest, so hopefully with the format string lab, you use GDB. Right? You've started to use GDB there, and it's a debugger. Okay, so GDB is actually really powerful. We can do lots of things. One thing we can do with GDB is, let's say that we wanted to get how to get opcodes. As you saw that in the PDF that we're inserting those opcodes, but maybe you want to, or the machine code, you want to get that. So one approach, although this is not for the lab, I'm just going to put it as a note on the side, how to get shellcode. Okay, so imagine you wrote a program, right? You wrote a program, myprog.c. And then you compile that. So you're going to do gcc-g-o, and then you call it myprog, and then you give it myprog.c. So that's the program that you gave it. Remember the -g flag is so that you can use GDB. So now you start the program and you're going to do, GDB /myprog. Right? You start the program and then, you're now in GDB itself. You're in GDB itself. And now if you want to, let's say, imagine that myprog.c has, a main. So it's got a main in there, right? Something like that. And you want to take a look at that main and focus just on that main, you can do disassemble. You can use disassemble main by the name. And now you'll be able to basically look at the disassemble version of it, which is getting the opcodes for the shell code. All right, so if you do that, then now the next step is you can say something like xbx main and then +10. That just indicates an offset from where the main starts, and that will now give you the opcodes. All right, and this is how you can go about getting that machine code that you can inject into other programs. So let's say, for instance, that you didn't want to do a shell, but you just wanted to do the calculator for whatever reason, right? You wanted to do the calculator. So then you'd write the program for the calculator in here, compile it, right? Run it, and then disassemble it, disassemble the subroutine in it that you actually want. And then with this command, xbx, you would be able to get the actual opcodes. And now you can just start collecting these, and that would give you, that shell code that we saw in exploit.c, the one that you're writing into the bat file. You'd be able to get that for yourself. However, thankfully that's given to us in this lab, and so we don't have to go into the details of that. But for those of you that are interested, you can follow this approach to try to obtain them. Are there any questions about that, guys?
No.
Okay. As you know, we are referencing assembler, but there's really no reason for us to go into assembler except to understand that it's sort of a midpoint, between the C code to assembler to machine code. Okay, so it's just different translations of how it works. Assembler is supposed to be a little bit more readable than the actual machine code. So it exists there, but people don't, prefer to obviously program in C or C++. Right, so we won't get into that detail either. So I talked a little bit about the basics of shell code, and really, yeah. So the instructions that you get, the actual opcodes over here, they're the things that look like this. So they look like, let's say 0x31, 0xc0, 0x31. So that's what I mean by those opcodes, right? And that you have that already in your PDF. Okay. right? So we've talked about the stack. Talked about this. So I'm just going through all my notes to make sure I've covered everything. Now, as far as getting the address, you might need a little bit of trial and error. Okay, so it's usually the hardest part. Okay, so getting the address. So as I said, this lab is pretty straightforward. You know, get the stack, get the exploit file. You're gonna run them, but when you run the exploit first. Exploit generates the bad file, then you run stack. Stack reads bad file, and then boom, you get a root shell. The trick is that you have to, before, write the code for exploit so that it correctly generates the code injection. So that's left to you. And obviously, one of those problems is getting the address. Now, we already defined that the address is an address in the stack itself. So that's where we're putting the shell code. You know, we're sort of putting both things in there at the same time. So how can you get this address, actually? So what are some suggestions? What would you guys say? How would you? Now, the address, by the way, will look like something like this. BF, FF, F4, OC, right? So they have this basic appearance, okay? So how do you think you can go about getting that address? What are some ideas that come to mind?
Through GDB.
Very good. Use GDB, right? You run exploit. First, you run exploit. Then, you know, you do ls-l, and you're going to see bad file in there. Then you compile the stack program, right? Run it with GDB. You see that? You run it with GDB. Okay, you run it with GDB. And then you're going to be in the GDB prompt. And now, just like you did in the format string lab, you can start looking at things in memory. So what was the command that you used to look for your name? So you remember in the format string lab, you wrote a command to find what was around the stack, around the pointer, right? So you wanted to find, you know, what's in there, where's my name? So what was that command in GDB that you used for that? Yeah, anyone?
To print.
Print what?
Print out the address to use print.
Yeah, but do you remember that I suggested that you guys use a command like this?
Oh, yes.
Like 20xw and then some kind of a register. Do you remember that? So
Oh,
this
yes.
allows you to look at the stack, right? And you did something like this. Well, as it turns out, and this will probably be very revealing, is that when you do something like x20, or sorry, actually not 20 this time, but bigger. If you remember, the code injection that you're doing is a lot bigger than 20, right? So you want to see more spaces in the stack. So if you did something like 120, 200, somewhere like that, you will see a bigger piece of the stack. And what I like about doing that is that if you look, it's all gonna look like hex, right? So imagine this is the output of running that command, right? So running, you know, x 120 xw esp, something like that. I'll give you another command that you can try. But imagine now this is what you see. And what's so great about it is that you can actually end up seeing the code injection, right? So if you're trying to figure this out, what would you look for of that code injection in this picture? What would you look for? What's something that's pretty common in the code injection that you're doing?
You can look for the no ops.
Very good. Excellent. You can look for the no-ops. It's very common, right? And so, you know, let me just use the 90 instead. You know, you'll have no 90, 90, 90, 90, 90, 90. And then somewhere in here, the address. It'll be buried in there, maybe harder to spot. And then somewhere in here, the code injection, the shell code, sorry, the shell code. But what's so great about looking for the shell code is that you know what the shell code looks like, right? Trying to see if I have it here. What are some of the things in the shell code? I have it here. 0x31, right? If you're looking at your lab, and then what? XC0, and then what? X50, and then, you know, and so on. So maybe you'll start finding those characters in there, and then you'll know, okay, I was successful. I'm able to load now. I'm able to load now by just doing this, right? By just doing that, you'll know that stack is indeed loading into memory because you found the no-ops. So that'll be a giveaway really quickly. That giveaway that, okay, I found it. And then after that, look for the address. Might be easier just to find the shell code in there. And then you'll know, okay, at least it works. I'm able to get the code in there. So that's a common problem that I usually see with this is that students get the code injection in there, but somehow they are not getting the terminal, right? And what if you're not getting the terminal, you're not getting a shell, it's probably that you have the wrong address, or you put the address in the wrong place, or you made a mistake in the code injection, although that's usually less common. It usually comes down to the address. Okay? Another command that you can try to visualize in there, the GDB is pretty good. In 1604, it's a lot better. You can also try 120i ESP. Okay? So try these approaches. This one might be a little bit better, so but I encourage you to try both. Certainly it'll help you. That's a I, by the way. Is this clear?
So what is I mean?
You'll have to look it up in the manual of GDB. So these are for writing. This presents the information in another way. I can't remember exactly, but I do remember that this actually works out a little bit better.
Okay.
You'll have to read the GDB help. All right.
Right.
So another technique that you might want to consider is if you have function names in your code, right? So if your code has function names, just like I showed you before, let's say you have stack.exe, and this contains several functions. One of them is actually called main. Okay, so if you have that and you want, and that's the function that you want, for instance, to look at, again, you can do gdb, and then you do, stack.exe, stat.exe, and then now you're going to be in GDB, so then you can do disassemble main. Remember, it's a module within that, disassemble main, and then it's going to dump the assembler code. And you might say, well, that doesn't help me. I don't really, you'll see like push, L, move, and that kind of terminology. But what's important to note is that over here, you'll see something, and these are addresses. So this is also something you want to take a look at. As you're exploring the addresses, really what you see there might be helpful. So again, I'm not really telling you how to solve this. I'm trying to let you figure that out, because it's like a, what do you call it? Scavenger hunt, right? So you're trying to figure out that address, but I'm giving you clues that might help you out a little bit. Okay. So what else? Right, so I talked about CSH already, so that hopefully should be clear that you will first use bash. Later on, when you tell me I've already figured it out with CSH, now I need to do it with bash, and then I'll give you the clues for that part as well. Okay, another command in GDB that you can try is p ampersand and then the name of a variable. Okay, so when you do that, just like you did over here with disassemble, this can give you the address of that variable. So that might be something of interest to you as you try to solve this. So you'll need to do a little bit of analysis there until you finally figured it out. That's why I'm trying to give you enough time. I'm expecting you guys from this point on, you really need to be done with set UID and format string correctly those labs. And on Thursday, I'm going to just give you that lab to work on buffer overflow, and I will just help you out with it. But you really need to solve it because, as I said, because of the practical exam, it's very important that it's pretty clear for you. All right, so a few other tricks. Let's see. All right, so the address. So let's talk a little bit about, so in exploit, so now I'm in exploit.c. right? And exploit.c, remember, the whole point of exploit.c is to produce bad file. You have a buffer in there, right? Let's call it buffer. And if you remember every example I've done, I put the address around here. Because you know that this is going to start overwriting some buffer that's only, size whatever, 12, 24. So you need to start writing there. But you need to align, this is your code injection. You need to align that code injection with the stack. So the stack would be this part here, right? So this is the stack. In memory. So you have that variable buffer in there, and you're gonna override it with all of this. That's pretty big. So you need to make sure that your address is completely in the right spot where the return address should be. It really doesn't matter what you put here. Doesn't matter because it's just overriding this space here, right? That's all it's doing. It's overriding this over here. But what really does matter is this. So how do you do it? What should you do? A lot of it is going to depend on whether buffer is size 12, 24, different sizes, right? So one simple way of avoiding complications is actually just write the address starting here. Start writing the address there and then just repeat it. So it's like write the address and then write the address again and then write the address again and then write the address again and then write the address, just keep writing it. But you need to leave some room for the no-ops because the NOP sled is going to help you. And then you need to write some other space for the shell code. Okay? And then here, whatever, more no-ops. Does this make sense, guys? Are there any questions? Guys, are you there?
Yes, we're
Yeah,
here.
we're here.
Are there any questions on this? Is it clear? Is it really all that clear?
Not for me, no.
No.
Not clear. Or no questions. All right, so now the trick is this. How do you write the address into buffer, right? So you have to write that code. So a simple way to do it is create a variable, char, call it address, a little buffer, and in there you're going to put your address in there. And notice you're going to write it exactly as I'm writing it here. Okay. So how does this work? Imagine that you write the address in reverse. So for instance, let's say that you've done all of your scavenger hunt and you figured out my address is the following. And here I'm going to be a little bit more precise. So my address is, so pay attention to this part because you'll have to do this. So my address, I've identified it is BF, FF, F3, D3. Something like that, right? Let's say that you figured out that's the address. So then the first thing you're going to do is you're going to take that address and you're going to write it into this buffer over here. Okay? And you're going to write it like this. So you're going to invert it. So now BF is going to be over here. So you just write XBF, indicate it's hexadecimal, then indicate it's hexadecimal, and you write, oops. And you're going to write, the next one is FF. So you can see this one goes there. That one goes there. Then you write the next one, F3. There. And then the last one is this D3. So you're going to do. Do you see that? Do you see that, guys? That's all you have to do. So in exploit.c, you will write this line of code basically like that. Char add xd3, xf3, xff, xbf. Right now, I'm just showing you. I'm not giving you the solution. You know, I'm just showing you the way that you write the code in there. Okay. Another one is you're going to take 4. Now, to write it into, so now that the question is, how do we write this whole thing into the buffer that we've created? And we called it buffer, right? So you need to create some kind of a for loop. So you can do for I equals 0 to I less than, and then this, call it n, where n could be, you know, size 12, 24, 36. You'll play around with that value to figure it out. And then you do I++. Okay, so then you're going to copy the contents of add, which is the one that we created here. Oops, I skipped one. So remember, that's the address variable. It contains your address. So you will copy this address into buffer. Now you could simply just do this, I, right? And you could do it like that. But that's just going to write it in the very first. It's just going to write until the size of address. So probably the n would have to be 4. And that's not going to work out. So what you want to accomplish is that you want to repeatedly write address in here. So you want to repeatedly write address. I write it there, then again, and again, and again, and then make, and then we're going to say that in the stack, the address, you know, I wrote over here several times, but see, these two align. And that's really what matters, that it's going to align with the address space, or where the address should be located in the stack. They need to align correctly and exactly, okay? So in the C code, you do this. And then now, because you want to repeat it, right? One trick that you could do is just do, you know, mod operation by 4, right? So if you remember your mods, it gives you a remainder, correct? So if I do, it's gonna go by index. So if I go from 1 to 24, right? It's gonna take, let's say, let me just do one example. So it would do 0, you know, %4 is gonna give you 0. Then you do 1, 4, it's gonna give you 1. You do 2, 4, it's gonna give you 2. 3, 4 is gonna give you 3, but then when you do the next one, 4, 4 is gonna give you 0. So in essence, this is the index, I. So I is that one, which is just this one here. And then you're just doing by the modulus operation by 4, and now you end up with this. So you literally can iterate through all the index positions in I from 0 to 24, but you're always just writing to it the 4 elements from your the 4 elements from your address from this variable, because this one only has 4, which is these 4. 1, 2, 3, 4. Make sense, guys?
Yeah.
That's another trick in the, remember, this is in exploit. In exploit.c, you're going to do that just to copy, and that will, so once you have your address, this code will take care of your, of writing that, you know, like I said, writing, you know, like little train cars, right? All of these, and as long as you've got the right size and they're aligned, you'll get your return address in there as you want it. Yeah, let me just finish this one. So if I do 5, 4, it'll be 1. If I do 6, 4, it'll be 2. I do 7, 4, it'll be 3. I do 8, 4, and now it goes back to 0. So as you can see, 0 to 3, 0 to 3, 0 to 3. So with this approach, I can just, out of these 4, I can repeatedly assign them to the index position of buffer, and I can effectively create that. Okay. Are there, this is something, I mean, you can write that code in various ways, but you know, I'm trying to help you, so I'm giving you that example. Are there any questions about that? Okay, no questions, so let's continue then. Right, so I said, so again, you know, very important one, how to get the return address. Return address. Okay, so remember GDB dot stack. Another way of doing this is you could do GDB, put a breakpoint, just make sure you put it in the right place. I'm not giving you the correct index. Let's say you have to pick that, then run it. And then in here, ESP, or you could try, 140, whatever, and try other registers. Remember, these are called registers, ESP, or possibly EBP. Okay, so I want you to really try all these things, but you want to start to, eventually it'll start to make sense, you know, which address or which one of these commands is most helpful. Now to run the program, it's usually GCC fno stack protector, right? So the thing that monitors the stack, -C exec. Oops. So these are all commands that you can use. Exec stack. And then your output dash, dash O prog from proxy. Okay, so that's a command. We talked about the exec shield. The instructions are in the handouts. we talked about all that. So really, you'll be doing until problem 2.1 initially, or task 1, 2.4. I really just want you to get that root shell using CSH. After that, the problems will go into bin bash and address randomization. Those are actually easier ones. You figured out the first one. But the main thing is to figure out how to get that return address. That's really the key thing that we have to figure out. All right, so let's see. I think I've given you all the commands at this time. All right, so the last part I'll give you is for that exploit to be complete. So you have, let's say this is a C program, right? So this is C, and then you have in there, number include string it. You have dot, 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 and then this is string dot H. And then you have a variable. This is from your PDF shell code. And that looks like, I'm not going to do the whole thing, but it looks like x31, xc0, and then it looks x50, and so on, dot, 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 all the way to xcd, x80. All right, so that's your shell code right there. Everything to the right of that, which is in a comment, if you notice, like that, is assembly. But it's just a comment, so it's going to be ignored completely. It's only there for reference. So now, given this code, you want to write that in there. So it's got a semicolon. And now in the main, in int main, you're going to take all the pieces that I gave you previously, and you're going to add them together. Okay, so you're going to need a buffer that you're creating, buff of size 517 or so, right? And then, you got the whole bat file thing. I'm going to skip that. I'm only going to focus on the parts that have to do with setting the buffer. So if you do mem set, that's, a buffer, you're referring to that buff. And then you mem set it to 0x90, which is the no-op for the entire length of it. All right. Then again, you do over here the address. So this is going to be x3, 0x F9, x FF, and then XBF. Just like that, right? So as we had discussed, the idea is that there's 4 of these that make up the address. So then once you have that, you're going to do a for loop for I equal 0, I less than n. You have to figure out that n, I plus plus. And then all you have to do is what I indicated, that buffer, buff, same buff over there, right? I equal address, this is that address. And then I percentage 4, right? And then that's it. You've added the address into buffer. Now the last part is, how do you add the shell code? So to add the shell code, which is this one, and that's shell code right there, you can do the exact same thing. You can take for I equals 0, I less than size of shell code, which is that shell code, I plus plus. Okay? And again, right? So in here, you just now copy, as you might imagine, into buff shell code. Right? And you probably just copy all of shell code. Keep track of this I, by the way. I'm using it quite a bit, so just make sure you got it in the right places. So plus I, and then here have an offset. What is that offset? That offset is that you're going to say, I want that I not there, not there, an offset that starts there. So that offset would be that size. Remember, the size is 517. The range is from 0 to 517. So pick a number in there, kind of play with it until you figure it out. And that's it. This is actually the code that goes in exploit. Oops. That is the code that goes in exploit.c. Okay, that's the code that goes there. Are there any questions about that?
No, not for me.
All right, great. So it sounds like it's making sense. All right, so as I said, I'm just trying to give you as much information as I can. Okay. So now to give you even more detail, kind of a summary, right? So now, summary, given all that information, what's the sequence of steps? Okay. 1, change SH from bash to CSH. Don't forget, when you're done with this lab and before you begin or turn off the computer, make sure you switch SH back to bash. Now, question is, compile, exploit, and stack. So let's start with stack. Okay, you do that. Now, question is, remember, when you're running these, do you run them as root or user? You have to figure that out, right? You have to keep that in mind at all times. Then you're going to have to compile exploit. Okay. Now, one of these needs to be chmod 4755. Right? What is that again? What is chmod 4755? What is that?
It's set UID, right?
Set UID, perfect, very good. Exactly, so it is chmod 4755 is set UID, very good. Now, which one of the two programs do we make set UID? What do you guys think? Do I make, so this is a very fundamental question, right? Do you make exploit this one set UID? Do you make stack set UID? Do you make both of them set UID? Do you make none of them set UID? So if you understand, again, once you, let me put it this way, once you understand what we're doing, you can easily answer that question. That's an understanding question. So which one?
Stack.
Stack. Why stack?
Because exploit just used just to create the bad file, and
Yes.
stack will execute it.
Very good. Excellent answer. And that's an important answer, right? To never forget that exploit is just for generating the bad file. It's really just like a utilitarian function, but it is really stack that is going to help you to, is the one that's has the vulnerability, is the one that you're trying to exploit. Very good. Then after that, you need to run the programs. You will run exploit first, that'll generate the bad file, and then you will run stack. And stack will read the bad file, and then it'll execute. Remember again, which one of these should you be running that as, right? So that's another concept that you need to explain really well. So what's going to happen when you run this? When you run it with this sequence of commands, you're going to get a message that says stack smashing detected. And that's because the compiler has some code that is detecting sort of what you're doing, and it's going to try to prevent you from doing it. So we have, these are the mechanisms that we need to disable, right? So if you remember, these are the mechanisms that we need to disable. And that's why the instructions indicate that you need to turn off randomization. So turn off randomization, exec stack, and you're going to turn off the stack protector, which is -fno stack protector. Okay, so you're going to be doing that. So hopefully once you do that, then you will be able to run this without the stack smashing, and then hopefully then you will get that also desirable terminal. And then once you get the terminal, you need to type ID or who am I, or both actually. And then that should tell you that you got the root privilege. Although once you see this, you know you were successful. But that's the idea anyway. Is that clear, guys? Now the commands for this, I don't need to write them down. They're in your PDF, so you can just find them there. Let's do some more examples. So let's say that you're trying to find that address, right? So you're trying to find out things. So you ran stack. Now you do GDB dot stack, and it's going to then, you're going to be in the GDB prompt. Break 15. I'm just going to pick another one, and then you can run it. All right, and now you're in there somewhere. And if you have variables in your program, you can also try to view them. So you'll have to play with this, but you can type something like p string, right? And if you remember, string is one of the arguments for the vulnerable program buff. Okay, so that might give you an address. And so that might be of interest to you as you start to figure out this lab. Any questions?
Nope.
All right, so that's pretty much it. I really want you guys to start working on this as soon as possible. So I can't delay the other homework assignments anymore, right? So those 2 assignments, or the format string one, is due this Thursday. And so please make sure that you submit it. Please make sure that you submit it, set UID. If you're having problems, you really need to get in touch with me, right? So I can help you out, because on this Thursday, I really just expect you to start working or advance quite a bit in buffer overflow, as we need to wrap up this topic, because probably next Tuesday, I will start web security, which is a completely different thing. So I might lecture in web security, but then leave the Thursday open for buffer overflow. So really, after today, I'm not going to give you any. I've given you everything pretty much. I'm making sure everything that I usually give students to solve this, and then that gives you time in the lab this Thursday and the following Thursday to work on buffer overflow. But just be aware that on Tuesday, I will lecture on the new topic, which is web security. And then also, I will just start going into the term project really quickly, because if you think about it, next week is week 5, and the project in this class is pretty involved. And so I usually motivate the project and then start with the whole sequence of web security lab. So it's the same principle: code injections and input validation. But because nowadays people develop a lot in C. I'm not going to say that they don't, but a lot of the like Facebook and all that stuff is really in the web. And so banking, you don't really have an app in your PC. What you have is a website, or you have an app in your phone, and that's almost like web development also. And so the focus of the project will be web security of a website, like an e-commerce site, where we can explore all of that. So I'll go over all of that next Tuesday, and then we'll start the labs after the exams are complete, your exams. Next week also, Tuesday, you'll form your term project groups of 3. So start thinking about people you want to work with. So we'll start all of that. So anyway, so my point is, sometimes if time permits, I go back to a couple of C labs towards the end of the semester, you know, what I would call like miscellaneous or special topics. But I take about 5 weeks, including exam time, 5.5, I guess, for this topic, which is the C related, C related labs leading up to buffer overflow. And so we are almost done. We are in fact done with the lectures. Also next Tuesday, I will probably just do a slide summary. So I have some slides on Blackboard and I'll probably just, but usually I end up, it's a lot of what I've already stated. So it's just a summarization, but I will go over that. I had forgotten that I haven't done that. Okay, so, but anyway, but probably we will also start web security in the project next Tuesday. Okay, so that's, let's see, I've given you pretty much everything. Yep, so that concludes my notes on, you know, kind of call it like a scavenger hunt, you know, the fun lab to find the return address. So I've given you all those materials. Now on Thursday, you will just work on the lab. It'll be an open lab and, you know, I'll be here. Just ask me questions about anything. Please, as I said, make sure that you've completed the format string and the set UID labs by Thursday. So you can then have 2 labs to work on: buffer overflow, summary lecture on Tuesday, plus probably the summary lecture won't take an hour and 40 minutes. So I will probably just start with web security and the project, form your groups already, and then just remember, after you finish the buffer overflow lab, then you have the written exam and the practical exam during week 6. Yeah, so I think that works out really well as far as our schedule. And then we'll start doing a new lab in web security on week 7. So that would be the plan. All right, so I don't have anything else to give you, so I'll stay here a few minutes for those of you that have questions. Otherwise, you know, please go work on these labs, and I will see you guys on Thursday. Thank you.
Hi, Professor. I have some question.
Go ahead.
I just still not very clear about the exploit.c program. Why you use I%4 to copy the shortcode to the buffer arrow?
It's one solution. You could have used other solutions. You could have done, you know, you could just do this. Okay, that's kind of, so you could have just, keep writing these. I mean, you don't have to. Let's say, just to simplify it, this is A, this is B, this is C, this is D, okay? So you could have just done A, B, C, D, and then again, A, B.
Why you will do that? Do it again?
What?
Why you do it again? Just
Why do I
ABCD.
repeat? That's your question. Why do I repeat? Okay,
Yes.
so the reason why I repeat is this, what I explained, right? That maybe if I write a new page. Okay, so remember, you have the stack, that's memory. You have a function in a frame there. Give me a sec.
Yes. Okay, what?
Yeah, hold on. So here's the frame, right? Here, we have the frame. And then we have things like that, right? Remember that we have a variable buffer. And then the return address would be somewhere around there. You are writing a code injection in bad file. That basically where buffer is, that's where you want to start your code injection. You see that? That's where it will start writing. However, all of this is wasted because really the only thing that you care about is putting a return address there. So really, when you do the alignment, right?
Right.
You want to put your return address here. And really,
Yes.
this would be no ops. Because
Yes.
that's how we did memset, right? And then the code injection, or the shell code, sorry, is somewhere around here, right?
Right.
So that's the idea. So what I'm doing is, instead of having to worry about figuring out where that, where to put it, where to put the return address, instead of having to do the work of figuring out, okay, well, I need to start at 24, or sorry, not 24. Let's say 12, and then put the address at 12 position, right? Instead of
Right.
worrying about that, I just kind of do the opposite. I just say, you know what? And also the fact that I know that this is wasted, so I might as well just start writing the address from here. So that way it's like I put the address there, and I put the address there, and I put the address here. But I know one of these will be aligned. It's just a simplification of putting the address instead of, you know, in case this buffer, it's the idea that maybe this buffer was 12 or 24, and I'm not clear on the size of it. So by not knowing
36.
how big that buffer is, because remember, if that buffer, let's say I have two stacks. I have two stacks, right? They're both buffer. But if one buffer is 12, then the return address, and let's say, and the other one's 24 in size, right? So this is buffer and buffer. So if that's the case, then the return address will be here for that one, and it'll be over here for that one. So there's an offset.
Yes, yes, I got it.
You get it now?
Yes, I just know the offset. Get the offset.
Offset is just, it just means that they're not aligned, right? Because this one is bigger than this one. So it pushes it further.
Yes,
Do you see that?
yes, I see that.
And that's why you just, okay, so you're gonna, you don't know, it's, you know, this could, let's say that buffer was a variable length variable, and sometimes is longer, sometimes it's shorter. So it would just make the attack a lot more difficult to align to the return address. So if you just, if you assume that buffer is always like a multiple of something, just keep adding them, not the whole thing, right? Because you need no ops and you need the shell code, but you're wasting this space anyway. Might as well fill it up with return addresses. Does that answer your question?
Just so why you repeat that for code? Because you just should for the memory.
Right.
Right.
Only one of them will actually take effect. The other ones are just garbage. They're not, they're being ignored. I mean, if you don't want to do it, don't do it. I mean, you don't have to. That's my point. So if you just want to know exactly where the address is, let's say that you say, you know what? I know the address for sure is in 24, right?
Yeah.
So then just do buffer 24 address 0, buffer 25, oops, address 1, and so on. You can do this in multiple ways. But the reason why I did it that way is just it just seemed more logical
Okay.
to fill up this. That way I know everything at the beginning is addresses. I have about 4 or 5 of those. And as long as they're, you know, they're usually bytes, right? So they're multiples of bytes. And so it, you know, you ensure that that at least one of these will be aligned. It's supposed to make it a little bit easier.
Okay, okay, got it, I think.
You got it now? Okay.
Yes.
But you do it, you know, if you don't want to do that, just leave this as NOPS and then just find out the precise number of where the address should start. You can also do that.
Yeah, yes.
Either way is fine. There's a lot of ways of doing this lab. It's really just, you know, I'm just
Okay.
trying to give you hints that might make your life easier.
Okay, okay. Okay, thanks.
No problem. Any other questions, guys?
I think just this.
Okay, great.
I guess. Thank you. Have a good day.
You too.